Picture this. You're lying in bed at 3 a.m., unable to sleep, and suddenly that question pops into your head. What was before the Big Bang? Your mind starts spinning. If everything started with the Big Bang, time, space, matter, energy, then what was before? But wait, if time itself started then, how can there even be a before? Congratulations. You just stumbled into one of the most mind-bending questions in all of science. Here's the thing that'll really mess with your head. Asking what came before the Big Bang might be like asking what's north of the North Pole. When you're standing at the North Pole, every direction is south. There's no more north to go to. Stephen Hawking loved this analogy, and honestly, it's brilliant. Time might work the same way at the Big Bang. There simply isn't a before because time itself begins there. But hold on. Scientists aren't satisfied with just throwing up their hands and saying the question makes no sense. Over the past few decades, they've developed some absolutely wild theories about what might have preceded our universe's explosive birth. And these aren't just late-night dorm room speculation. These are serious mathematical models backed by some of the brightest minds in physics. Why this question matters more than you think. You might wonder why scientists spend so much time thinking about something that happened 13.8 billion years ago. Well, here's why it matters. The conditions before the Big Bang, if such a thing exists, set up everything that came after. Every atom in your body, every star you see at night, the very fabric of space and time you move through, all of it was determined by what happened in those first impossibly tiny fractions of a second. Think about it like this. Imagine you're watching a movie that starts with a massive explosion. Sure, the explosion is dramatic, but wouldn't you want to know what caused it? What was the setup? The backstory? That's exactly what cosmologists are trying to figure out. And this isn't just academic curiosity. Understanding the origin of the universe helps us understand fundamental questions about reality itself. Are the laws of physics inevitable? Or could they have been different? Is our universe unique or one of many? Could the Big Bang happen again? Let me share something that'll blow your mind. Recent experiments with ultra-cold atoms, we're talking temperatures just a hair above absolute zero, have actually demonstrated something called false vacuum decay. Scientists in Italy cooled atoms down so much that they could watch bubbles form from quantum vacuum fluctuations. It's not exactly the same as creating a universe, but it shows that something from nothing isn't as crazy as it sounds. The classic Big Bang problem. Here's what the traditional Big Bang theory tells us. About 13.8 billion years ago, all the matter and energy in the universe was compressed into a point smaller than an atom. Actually, scratch that. It was compressed into a point with literally zero size. Physicists call this a singularity, and it's where their equations basically throw up error messages and quit working. At this singularity, the density of matter was infinite. The temperature was infinite. The curvature of space-time was infinite. See the problem? Infinity isn't really a number. It's more like a mathematical way of saying we have no idea what's going on here. But here's where it gets even weirder. According to Einstein's general relativity, space and time are woven together into something called space-time. They're not separate things. They're aspects of the same fabric. So if the universe began at the Big Bang, then space-time itself began at the Big Bang. There was no space outside for the Big Bang to happen in. There was no time before for anything to exist in. This drives people crazy, and for good reason. Everything in our everyday experience has a cause. Your coffee gets hot because you heated it. Rain falls because water vapor condenses. But the Big Bang? According to the classic model, it just happened. No cause, no reason. It's like the ultimate free lunch, an entire universe popping into existence from absolutely nothing. Actually, Alan Guth, one of the most important cosmologists of our time, literally called it the ultimate free lunch. He proved mathematically that the total energy of a universe might actually be zero. How? Because the positive energy of matter is exactly balanced by the negative energy of gravity. Mind-blowing, right? Enter inflation, the game changer. In the early 1980s, physicists had a breakthrough that completely changed how we think about the Big Bang. They realized the bang might not have been the beginning at all. Instead, it might have been more like a transition from one phase of the universe to another. This idea is called cosmic inflation, and it's absolutely wild. Imagine blowing up a balloon, but instead of using your lungs, you use something that doubles the balloon size every tiny fraction of a second. In less time than it takes light to cross a proton, the universe expanded by a factor of at least 10 to the 26th power. That's a 1 followed by 26 zeros. To put this in perspective, imagine a grain of sand suddenly expanding to become larger than the entire observable universe. Now imagine that happening in a time so short that calling it a moment is generous. That's inflation. But here's the key insight. This inflationary period might have been going on before what we call the Big Bang. The hot, dense state we associate with the Big Bang might just be what happened when inflation ended in our particular region of space. The inflation field decayed, dumping its energy into particles and radiation, creating the hot cosmic soup that eventually became stars, galaxies, and us. What's really mind-bending is that inflation might still be happening somewhere. While inflation ended in our observable universe 13.8 billion years ago, it might be continuing in other regions, constantly creating new pocket universes. We'll come back to this idea because it leads to one of the most controversial concepts in modern physics, the multiverse. Cycles within cycles, the eternal return. Now, what if I told you that some scientists think the Big Bang wasn't the beginning, but just the most recent in an endless series of cosmic rebirths? This idea isn't new. Ancient Hindu cosmology described the universe as going through endless cycles of creation and destruction. But modern physics has given this old idea new mathematical teeth. These are called cyclic models, and they completely sidestep the whole what came before question by saying there's always been a before. Picture the universe like a phoenix, dying in fire only to be reborn from its own ashes. Except instead of fire, we have a big crunch where the universe contracts back down, followed by a big bang that starts the next cycle. But wait, you might think, doesn't the universe's expansion seem to be speeding up? How could it ever contract? That's a great question, and it's exactly why the old cyclic models fell out of favor. But newer versions have found clever ways around this problem. Some models suggest that what we perceive as the Big Bang is actually a collision between parallel universes floating in higher dimensional space. These collisions happen periodically, each one creating what inhabitants of that universe would experience as a Big Bang. The universes bounce apart, slowly drift back together over trillions of years, and then collide again. Roger Penrose, who won the Nobel Prize in Physics, has an even stranger cyclic model. He suggests that the infinitely far future of one universe becomes the Big Bang of the next. When all the black holes have evaporated and all matter has decayed into radiation, the universe forgets about size and scale. Through some mathematical magic I won't pretend to fully understand, this end state becomes identical to a Big Bang singularity, starting the whole process over again. Penrose even claims we might see evidence of previous cycles in the cosmic microwave background, that faint afterglow of the Big Bang that fills all of space. He's identified circular patterns that he says could be the scars left by colliding black holes in the previous universe. Most cosmologists are skeptical, but hey, the man has a Nobel Prize. You can't just dismiss him as a crackpot. Quantum foam, and the fuzzy beginning. Ready for things to get really weird? At the smallest possible scales, we're talking about distances billions of times smaller than a proton. Space and time might not be smooth. Instead, they might be foamy. This idea comes from quantum mechanics, the bizarre theory that governs the subatomic world. According to quantum mechanics, nothing sits still. Everything jiggles. Even empty space seethes with energy, with particles popping into existence and disappearing faster than anything can measure them. John Wheeler, the physicist who coined the term black hole, proposed that at the tiniest scales, these quantum fluctuations would affect space-time itself. Space would bubble and froth like the foam on a cappuccino. Time would lose its meaning, with past and future getting scrambled together. In this quantum foam, the normal rules break down. Cause and effect become meaningless. A particle could travel backward in time, cause its own creation, and nobody would bat an eye because before and after don't really exist at this scale. Some physicists think the Big Bang might have emerged from this quantum foam, a random fluctuation no different from the countless others happening all the time, just happened to inflate into an entire universe. In this view, universes might be popping into existence all the time like bubbles in boiling water. Most immediately collapse back into nothing, but occasionally one catches hold and expands into something like our cosmos. NASA has actually tried to detect signs of this quantum foam using X-ray telescopes. By looking at light that's traveled for billions of years from distant quasars, they hope to see distortions caused by the foamy nature of space-time. So far, they haven't found anything, but the search continues. String theory's take: everything is vibration. If you thought things couldn't get weirder, let me introduce you to string theory. According to this idea, everything in the universe, matter, forces, space, and time, comes from tiny vibrating strings. These strings are so small that if an atom were scaled up to the size of the solar system, a string would still be smaller than a tree. String theory needs extra dimensions to work, up to 11 of them. We only see 3 dimensions of space because the others are curled up too small to detect. It's like how a garden hose looks like a one-dimensional line from far away, but up close you can see it has a circular dimension wrapping around. In string theory's version of the early universe, there might never have been a true singularity. Instead, when you trace time backward, the universe shrinks until it reaches a minimum size, the size of a string, and then bounces back. The Big Bang wasn't a beginning, but a bounce. Even cooler, string theory suggests something called T-duality. This means that a universe with a very small radius is physically identical to one with a very large radius. So as our universe contracts toward the Big Bang, from another perspective, it might actually be expanding. The Big Bang singularity might be an illusion caused by looking at things from the wrong angle. String theorists have developed something called pre-Big Bang cosmology. In this model, the universe started out cold, empty, and almost infinitely large. Quantum fluctuations caused some regions to begin contracting. As they contracted, they heated up and eventually reached the hot, dense state we call the Big Bang. But this wasn't a beginning, it was just a phase transition like water turning to ice. This might sound like pure speculation, but string theory makes specific predictions about what we should see in the cosmic microwave background. As our measurements get more precise, we'll be able to test whether string theory's version of the pre-Big Bang universe is correct. All right, buckle up because we're about to dive into the deep end of theoretical physics. Remember how I mentioned that inflation might still be happening somewhere? Well, that leads us to one of the most mind-blowing ideas in modern cosmology. We might be living in a multiverse. I know. It sounds like something out of a Marvel movie. But this isn't science fiction. It's a serious scientific hypothesis that many physicists think is not just possible, but probable. The eternal inflation problem, or is it a feature? Here's the thing about inflation that will scramble your brain. In most models, once it starts, it never completely stops. Sure, ended in our region of space 13.8 billion years ago, but the inflationary field is unstable. Random quantum fluctuations mean that while inflation ends in some regions, creating pocket universes like ours, it continues in others. Picture it like a pot of boiling water, but cosmic. Bubbles form where inflation has ended. These are universes like ours. But the water between the bubbles keeps boiling, keeps expanding exponentially. New bubbles constantly form, each one a new universe with potentially different physical properties. Alan Guth, who helped develop inflation theory, puts it bluntly. It's hard to build models of inflation that don't lead to a multiverse. Think about that for a second. One of the creators of the theory is basically saying we tried to explain our one universe and accidentally predicted infinite universes. In this eternal inflation scenario, our entire observable universe, all 93 billion light years of it, is just one tiny bubble in an infinite froth of universes. And here's the kicker. Each bubble might have different laws of physics. You see, the values of physical constants, things like the strength of gravity, the mass of electrons, the speed of light, might be determined by random quantum events during the transition from inflation to normal expansion. It's like each universe rolls cosmic dice to determine its fundamental properties. Most of these universes would be sterile. Stars couldn't form or would burn out in seconds. Atoms might not even be stable. But in an infinite multiverse, even incredibly unlikely combinations would occur. And naturally, we find ourselves in one of the rare universes where conditions allow for stars, planets, and life. Where else could we be? The many worlds where quantum gets cosmic. But wait, there's another completely different type of multiverse, and this one comes from quantum mechanics. Ever heard of Schrodinger's cat? The thought experiment where a cat in a box is both alive and dead until you open it? Well, one interpretation of quantum mechanics says the cat really is both alive and dead in parallel universes. This is called the many worlds interpretation, and it's been around since 1957. Every time a quantum event could go multiple ways, the universe splits. In one branch, the radioactive atom decays and the cat dies. In another branch, it doesn't decay and the cat lives. Both branches are equally real. Now, quantum events are happening constantly. Every particle interaction, every photon absorption, every radioactive decay creates a new split. The number of parallel universes grows exponentially, branching into an unimaginable tree of realities. Actually, let me stop here and address something. You might be thinking this sounds completely insane. Parallel universes where every possible outcome happens? Where there's a version of you who became a rock star, another who became president, and another who decided to have pizza instead of a sandwich for lunch. I get it. It sounds crazy. But here's the thing. The many worlds interpretation solves a lot of problems in quantum mechanics. It explains why quantum experiments give probabilistic results without requiring any mysterious collapse of the wave function. Everything that can happen does happen. We just only experience one branch of reality. And when you apply this to cosmology, things get even wilder. All those quantum fluctuations during inflation. In the many worlds view, every possible pattern of fluctuations happened in some branch of the wave function. There are universes where galaxies form differently, where stars are distributed differently, where Earth never formed, where life never evolved. We're not just one universe in a multiverse. We're one branch in an infinite tree of quantum realities, nested within one bubble in an infinite foam of inflating space-time. Starting to feel small yet? The string theory landscape, 10 to the 500th power possibilities. String theory adds yet another layer to the multiverse cake. Remember those extra dimensions I mentioned? Well, they can be curled up in different ways. Imagine a piece of paper. You can roll it into a cylinder, fold it into a triangle, crumple it into a ball. Each gives a different shape even though it's the same paper. The extra dimensions in string theory can curl up in about 10 to the 500th power different ways. That a 1 followed by 500 zeros, a number so large that if you tried to write it out, you'd run out of atoms in the observable universe before you ran out of zeros. Each way of curling up these dimensions gives different physical laws. Different particles, different forces, different constants. String theorists call this the landscape of possible universes. If eternal inflation is happening, then different bubbles might land in different parts of this landscape. Our universe happened to land in a region where the constants allow for chemistry, stars, and life. But most bubbles would land in regions where the laws of physics are completely different. Some physicists hate this idea. They wanted string theory to predict exactly one possible universe, ours. Instead, it predicts a vast landscape of possibilities, and we need the anthropic principle. We observe this universe because we can exist in it to explain why we see what we see. But others embrace it. Leonard Susskind, one of the fathers of string theory, argues that the landscape multiverse is actually a prediction of string theory combined with inflation. If both theories are right, then a multiverse isn't just possible, it's inevitable. Observational hints. Can we see other universes? Now, for the million-dollar question. Is any of this testable? Can we actually detect other universes? Maybe, just maybe. If another bubble universe collided with ours in the distant past, it might have left a mark, a circular pattern in the cosmic microwave background. Some researchers claim they've found such patterns, though the evidence is controversial. More intriguingly, if eternal inflation is real, it makes specific predictions about the statistical properties of the cosmic microwave background. The patterns we see should follow certain distributions that depend on how inflation works. Here's something that happened recently that's pretty amazing. Scientists studying the cosmic microwave background found what they call the cold spot, a region of space that's inexplicably cooler than it should be. Some physicists have suggested this could be evidence of our universe colliding with another bubble universe billions of years ago. Most scientists are skeptical, but it shows we're actually looking for evidence. There's another wild possibility. If parallel universes in the quantum sense exist, they might occasionally interfere with each other. Some researchers are designing experiments to look for such interference. Imagine detecting the gravitational influence of galaxies that exist in a parallel quantum branch. It sounds like science fiction, but the math says it might be possible. Loop quantum gravity. Space itself has atoms. Let me introduce you to another mind-bending theory, loop quantum gravity. While string theory gets most of the press, loop quantum gravity is a competing theory that's just as wild. According to loop quantum gravity, space itself is quantized. Just like matter is made of atoms, space is made of tiny, indivisible chunks. These atoms of space are incredibly small, about 10 to the minus 35th power meters across. But they're not nothing. They're the smallest possible units of space that can exist. This changes everything about the Big Bang. See, if space is made of discrete chunks, then the universe can only compress so far. It's like trying to compress a box of marbles. Eventually, the marbles are touching and you can't compress any further. In loop quantum cosmology, when you trace the universe backward, it contracts until it reaches maximum density. One space atom per per space atom of volume. Then quantum effects cause it to bounce back, starting a new expansion phase. Martin Bojewald, one of the pioneers of this field, has shown that you can actually trace space and time through the bounce. The universe before the bounce is real and calculable. The Big Bang wasn't a beginning. It was a quantum bounce from a previous contracting universe. What's really cool is that loop quantum cosmology makes specific predictions. The quantum bounce should leave signatures in the cosmic microwave background, specific patterns in how matter clusters on the largest scales. As our observations get better, we'll be able to test whether the Big Bang was really a big bounce. The no-boundary proposal, when time becomes space. Stephen Hawking had a different solution to the beginning of time problem, and it's absolutely brilliant in its simplicity. He said, what if there is no boundary? What if asking about the beginning of time is like asking about the edge of the Earth? The Earth's surface has no edge. It's finite but unbounded. You can travel in any direction and never hit a wall. Hawking proposed that time might be similar. As you go back toward the Big Bang, time gradually becomes more space-like until there's no distinction between time and space. There's no first moment because time smoothly curves back on itself. This is called the no-boundary proposal. It uses something called imaginary time. Don't worry about the name. It's just a mathematical technique where time is treated as a complex number. In imaginary time, the universe's history looks like a four-dimensional sphere with no edges or boundaries. In this picture, the universe didn't begin, it just is. Asking what came before the Big Bang is like asking what's south of the South Pole. The question assumes a boundary that doesn't exist. What I find fascinating about Hawking's proposal is that it makes the universe completely self-contained. It doesn't need a cause or a creator. The laws of physics alone are sufficient to describe everything, including the origin of time itself. False vacuum decay. Creating universes in the lab? Here's something that might keep you up at night. Our universe might not be stable. We might be living in what's called a false vacuum, a state that seems stable but isn't really. Think of it like a ball sitting in a valley on a mountain. The ball seems stable, but if it gets knocked hard enough, it could roll into a deeper valley below. Our universe might be that ball, and the valleys represent different vacuum states with different physical constants. If our vacuum is false, then someday, somewhere, a quantum fluctuation could nucleate a bubble of true vacuum. This bubble would expand at the speed of light, destroying everything in its path and replacing it with a new universe with different physical laws. But here's the flip side. This same process might be how our universe began. Maybe what we call the Big Bang was just a false vacuum decay event in some parent universe. A quantum fluctuation created a bubble, our bubble, which expanded and became everything we know. Recently, scientists in Italy actually demonstrated false vacuum decay in ultra-cold atoms. They cooled atoms to less than a microkelvin above absolute zero and watched bubbles form from vacuum decay. It's not the same as creating a universe, but it shows the physics is real. Some physicists have even speculated about creating universes in the laboratory. If we could create the right conditions, extreme density, extreme temperature, might we trigger the formation of a baby universe? It sounds insane, but the physics doesn't explicitly forbid it. The baby universe would pinch off from ours, expanding into its own space without affecting us. We'd be cosmic parents, never able to communicate with our offspring universe. The information paradox. Is everything a hologram? Here's one more mind-blowing idea before we wrap up this section. The holographic principle. Some physicists think that all the information in our three-dimensional universe might actually be encoded on a two-dimensional surface at the boundary of space. It's like a hologram. A holographic image looks three-dimensional, but all the information is actually stored on a flat surface. Our universe might be similar. What we perceive as 3D reality might be a projection of information stored on a distant 2D surface. This connects to black holes and something called the information paradox. When matter falls into a black hole, where does the information go? Hawking showed that black holes evaporate, but if information is destroyed in the process, it would violate quantum mechanics. The holographic principle suggests a solution. The information isn't destroyed because it was never really inside the black hole. It's encoded on the event horizon, the boundary of the black hole. If this principle applies to the whole universe, then the Big Bang might be better understood as a kind of holographic projection. The real action might be happening on some boundary surface, and what we call the universe is just the holographic image. Some physicists are taking this even further. They suggest that space and time themselves might be emergent phenomena, like how temperature emerges from the motion of atoms. At the deepest level, reality might be made of something else entirely, something we don't have words for yet. So here we are. We've traveled through infinite multiverses, bounced through cyclic cosmologies, vibrated with cosmic strings, and gotten lost in quantum foam. Your brain probably feels like it's been through a blender. Mine certainly does, and I write about this stuff. But what does it all mean? And more importantly, why should you care? The cosmic perspective. You're more special than you think. First, let's address the elephant in the room. If there are infinite universes, if everything that can happen does happen somewhere, doesn't that make our existence meaningless? Aren't we just one random accident among countless others? I'd argue the opposite. The fact that it takes such extraordinary conditions to create a universe where we can exist makes our presence here even more remarkable. We're not just lucky, we're astronomically, inconceivably lucky. Think about it. If the strength of gravity were just slightly different, stars wouldn't form. If electromagnetic force were a bit stronger or weaker, chemistry wouldn't work. If the early universe had been just a tiny bit smoother or lumpier, galaxies and planets never would have formed. Whether you believe this is because we're in one lucky universe, or because all possible universes exist and we naturally find ourselves in one that supports life, the fact remains, we're here against all odds, able to contemplate our own existence and the nature of reality itself. Carl Sagan once said, "We are a way for the cosmos to know itself." That's profound no matter how many universes there are. What this means for science. The multiverse and these pre-Big Bang scenarios represent a fundamental shift in how we do cosmology. For centuries, science has been about explaining what we can observe. But now we're grappling with theories that predict things we might never be able to observe directly. Is it still science if we can't test it? This is a hot debate among physicists right now. Some argue that if a theory makes any testable predictions, even if we can't test all of it, it's still scientific. Others worry we're drifting into metaphysics, making up untestable stories about reality. Personally, I think we're in transition period. Just like it took decades to test Einstein's predictions about black holes and gravitational waves, it might take decades or centuries to test ideas about the multiverse or pre-Big Bang scenarios. But that doesn't mean we should stop thinking about them. The history of physics is full of crazy ideas that turn out to be true. Quantum mechanics seemed insane when it was first proposed. The idea that space and time could bend seemed like fantasy. Black holes were considered mathematical curiosities that probably didn't exist in nature. Now we have pictures of them. Practical implications. Yes, this stuff matters. You might be thinking, okay, this is all fascinating, but does it actually matter for my daily life? Actually, yes, but maybe not in the way you'd expect. Understanding the quantum vacuum and false vacuum decay isn't just academic. These concepts are crucial for understanding particle physics, which drives developments in everything from medical imaging to quantum computing. The Large Hadron Collider, which smashes particles together to study the early universe, has led to advances in superconducting magnets, grid computing, and even cancer treatment. The mathematical techniques developed to study the multiverse and string theory have applications in condensed matter physics, which is crucial for developing new materials. Some of these materials might revolutionize electronics, energy storage, or even room temperature superconductors. But beyond the practical applications, this research shapes our worldview in profound ways. Understanding our cosmic origins affects how we see ourselves, our place in the universe, and our future as species. The big questions that remain. Despite all these theories, massive questions remain unanswered. Here are some that keep physicists up at night. Why is there something rather than nothing? Even if the universe arose from quantum fluctuations, why do quantum fields exist at all? Why are there laws of physics in the first place? Is mathematics discovered or invented? The universe seems to follow mathematical laws with incredible precision. Is math a human invention that happens to describe reality, or is it the fundamental language of nature? What determines the constants of nature? Why does the electron have the mass it does? Why is gravity so much weaker than the other forces? Are these values random, or is there some deeper principle that determines them? Can information be created or destroyed? The holographic principle and black hole physics suggest information is fundamental, maybe even more fundamental than matter or energy. But what exactly is information in a physical sense? Is consciousness fundamental? Some interpretations of quantum mechanics seem to require conscious observers. Could consciousness be a basic feature of reality, like mass or charge? And if so, what does that mean for the origin of the universe? Where do we go from here? The next few decades are going to be incredible for cosmology. Here's what's on the horizon. Better observations of the cosmic microwave background might reveal signatures of other universes or evidence of what happened before the Big Bang. The Simons Observatory and other next-generation telescopes will have unprecedented sensitivity. Gravitational wave detectors like LIGO and LISA might detect signals from the very early universe, possibly even from the Big Bang itself. These ripples in space-time could carry information about pre-Big Bang conditions. Quantum computers might let us simulate the early universe in ways that are impossible with classical computers. We might be able to test quantum gravity theories by simulating quantum spacetime. Laboratory experiments might create conditions similar to the early universe. We're already creating quark-gluon plasma, the state of matter microseconds after the Big Bang. Who knows what we'll be able to recreate in the future? New theoretical breakthroughs could revolutionize our understanding. Maybe someone reading this will develop the theory that finally explains what came before the Big Bang. The human side of cosmic questions. You know what strikes me most about all this? It's that humans, barely down from the trees in evolutionary terms, living on a tiny rock orbiting an ordinary star, have figured out so much about the universe's origin. We've measured the age of the universe to within 1% accuracy. We've detected gravitational waves from colliding black holes billions of light years away. We've photographed the cosmic baby picture in the microwave background. But for all our knowledge, mystery remains. And honestly, I think that's beautiful. If we knew everything, if we had all the answers, what would be the point? The mystery is what drives us forward. I remember the first time I really grasped the scale of these questions. I was maybe 12, lying on my back in the backyard, looking at the stars. Suddenly it hit me. Those points of light were suns, maybe with planets, maybe with people looking back. and our sun was just one of billions in our galaxy, which was one of trillions in the universe. I felt incredibly small, but also part of something incomprehensibly vast. That feeling, that mix of awe, curiosity, and vertigo is what cosmology is all about. It's about pushing the boundaries of what we can know, even when those boundaries seem to stretch into infinity. The ultimate mystery. Here's the thing that really gets me. Every answer in cosmology seems to lead to bigger questions. We figured out the universe is expanding, but that led to questions about dark energy. We developed inflation to solve problems with the Big Bang, but that led to the multiverse. We're trying to understand the multiverse, and who knows what that will lead to. Maybe that's the point. Maybe the universe, or multiverse, is structured in such a way that there's always another layer of mystery. Maybe complete understanding is impossible, not because we're limited, but because reality itself is infinitely deep. Or maybe, just maybe, someone will have a breakthrough that makes everything click into place. A theory of everything that explains not just how the universe works, but why it exists at all. Wrapping up, the beginning of everything. So, what was before the Big Bang? The honest answer is we don't know. But we have amazing ideas. Maybe it was eternal inflation, creating endless pocket universes. Maybe it was a previous universe that contracted and bounced. Maybe it was a collision between higher dimensional membranes. Maybe time itself loops back, making before meaningless. Maybe it was quantum foam fluctuating in ways we can barely imagine. Or maybe it's something we haven't thought of yet. Something so foreign to our current understanding that we don't even have the concepts to describe it. But here's what I find most extraordinary. We're asking the question. A collection of atoms that coalesced on a planet 4.5 billion years ago has become conscious and is now trying to figure out where all the atoms came from in the first place. Whether there's one universe or infinite universes, whether time had a beginning or extends eternally into the past, whether we're alone in the cosmos or one of countless civilizations pondering these same questions, the fact that we can ask what came before the Big Bang is itself a kind of cosmic miracle. The universe has evolved creatures capable of understanding the universe. And maybe, just maybe, that's the whole point. So the next time you're lying awake at 3 a.m., mind spinning with these cosmic questions, remember, you're not just thinking about the universe. In a very real sense, you are the universe thinking about itself. And that's the most mind-blowing thing of all.